e minus 11. Oops, not squared. I was like, why do I square that? There we go. And it's clever about this. It's dividing by the whole number. It doesn't just divide by this and then multiply by 10 to the minus 11th, right? Cheat sheet. Okay. So that's one. Let's do one with the other one. What did I get? Okay. So what about a geosynchronous orbit? What is a geosynchronous orbit? Now we're getting into the fun stuff, right? Synchronized with the Earth. So we use these all the time, don't we? Okay. You guys have a satellite dish at your home, and the satellite dish just points to one spot in the sky, right? So it's like, how does that satellite stay still and over a point on the Earth, right? This is what somebody who isn't aware that the Earth is rotating asks, right? But really, what is it doing? It's really far enough away that the time it takes to go around once is what? A day. But you got to be careful because the time it takes the Earth to rotate once on its axis is not 24 hours. What is it? Look at your sheet of everything. I just gave you a sheet. Look at the side that has all the solar system things there, right? Look at the rotation period for the Earth. 56 minutes, 4 seconds. Why is that? Why is it 23 hours, 56 minutes, 4 seconds? It's not daylight savings time, okay? It's not a leap year, because that would be a hell of a lot more than a leap year, right? Okay? What is it? Do we know? We don't know. Remember that the Earth is doing two types of motion all at once. I will try to simulate this without breaking my bones, okay? It is revolving. Okay, so let's say Laura is the sun. Okay, we in this class are all orbiting her, attracted to her, yet not able to reach her because of our tangential velocity, right? It's kind of racy, right? Okay, so there we are. I'm orbiting her. I am revolving about her, which means I'm going in a big circle like that. That's what astronomers call that revolution, right? I am also rotating. Rotation happens about an axis within my body, right? Okay, now, as you look from the North Pole of the Earth, okay, the Earth is rotating. Well, as we look at it, it's rotating anti-clockwise, and I know this because if, say, the windows are the sunshine, the East Coast sees the sun first, right? That's the way you can always remember it. Yeah, the East Coast sees the sun first, so it's rotating anti-clockwise, right? And then the other thing is that as we look at it from the North Pole, it's rotating anti-clockwise. It is itself moving anti-clockwise around the sun. Okay, it is itself. Now, it is, of course, tilted on its axis as this thing depicts, right? Okay. But there it is, right? So its motion, and if you look at that sheet that I gave you, ones that are retrograde spin the other way. Everything in the solar system goes anti-clockwise around the sun, as seen above the North Pole of the Earth, or more or less, right? Everything goes anti-clockwise, but some of them spin actually clockwise on their own axis. That's retrograde. Normal motion is like this. So I'm going to try to walk around Laura, okay, and also rotate. Are you ready? So right now it's high noon. Remember, 24 hours is the time from high noon to high noon, correct? Okay, so it's high noon, day one, right? And now I'm going to walk this way. I'm also going to rotate this way, right? Are we ready? Here we go. Right now it's 23 hours, 56 minutes, 4 seconds. I've completed one revolution, haven't I? I'm in the same angle position with respect to the stars or the room, right? But do I see Laura Scotese right there? No. No, I don't. Okay. 24 hours, yeah? So there's two different days, right? There's a solar day or whatever, right? And there's a sidereal day. Astronomers have watches that are like sidereal watches. And the cool thing about that is, I mean, you look at the watch and it's always wrong, except for like on 2 times a year or something like that, right? Okay, this watch is always wrong, but the cool thing about sidereal time is that it corresponds to where the position of the planets, and not the planets, but the stars, right? At a particular time, sidereally, at your zenith, a particular star is up overhead, right? So, yeah, that's kind of fun. Connor's like, my brain is full. No, you can't stop. Just push it all in. Open your brain. Ah! Push that knowledge down in there harder. Close the brain up, you know. It hurts my brain. Okay, so we want to find the radius of a geostationary orbit. Are we ready for this? So what do we know? Don't we know the period is 23 minutes, 23 hours, 83 minutes, 23 hours, right? 56 minutes, 4 seconds, yes? Don't we know that? Right? So let's turn that into seconds. Go 23 times 3600 plus 56, 56 times 60 plus 4, right? That's how you go. Or if your calculator has degree minutes seconds conversion, by the time you've learned how to do that, you might as well do this. Okay, but there you have it. What do you get? 86164, that's what it is. Okay, so 23 times 3600 plus 56 times 60 plus 4. I'm going to store that in. I'm going to store that in A just for fun. 86164. There we go. So now we know the period is that. Don't we know the mass is that of the Earth, right? 5.97 E24 kilograms. And that's all we need to know, isn't it? So we want to solve for T. What's our first step in all of these things solving? Do we cross multiply? Is that what we did the last 3 times we did this? Yeah, so let's cross multiply, right? I'm just going to cancel the satellite mass, right? And I'm going to go 4 pi squared r. What's 4 pi squared r times r squared? It's cubed, baby. It doesn't cancel. People always want to cancel that way. Okay, that's Satan making you want to cancel that way. Okay, GMC t squared. Yes.
Hi.
Hello.
Do you have Kelsey Dunnigan in this class?
Kelsey Dunnigan is in my 3B class.
Okay.
Yeah.
Thank you.
Yeah. Sorry. Are we good? Are we good so far? We haven't made any mistakes. And then how are we going to solve for r? Are we going to divide, and then we're going to have to do what? This is the worst one. We're going to have to cube root, right? So I'm going to divide by 4 pi squared, right? And now to get the answer, I have to do a cube root, yeah? There it is, right? So how do you do a cube root, by the way? Do you just go into math and it's there? Yeah, you can do that. You can go into math and there it is. You can also, by the way, if you forget that, you can raise something to the 1/3 power, can't you? Yeah, this always works. But I'm gonna go ahead and use the fancy math function there. Okay, so this is going to look like in our calculator. I'm going to go cube root. I'm going to go ahead and use that, right? And then we have to go 6.67 e minus 11 times 5.97 E24, right, times 86164 squared. Okay, now we have to be very careful because we want to divide by 4 and pi squared, and very few students know that you have to put those in parentheses if you want to divide by both of them, right? So I've got to go divided by parentheses 4 times pi squared, right parenthesis that ends this, right? These guys match each other. These guys make the denominator. If you say divided by 4 times pi squared, it will divide by 4, then multiply the result of that division by pi squared. Now, what's sort of funny about this is pi squared is roughly 10. So you think you've made a power of 10 error, but you've made a I don't understand how to type things into calculators error. Okay? So try this. Let's calculate this in our calculator. In our calculator. Math. Okay, so math 4. Yes, math 4 is correct, right? All right. So 6.67. Who remembered that it was math 4? That's kind of amazing. Okay. Times 5 point. Calculate along with Mr. Murray. 5.97 seconds. 8,006. Huh? Some dang smart alecky kids.
Good. Where did you get 5.97?
Whoa.
That's the mass of the Earth. I looked it up on a book that I bought. 86164. Yeah, 86,164 seconds. Don't forget to square that, right? Divided by 4 times. I know you don't have to say times pi squared, but I always like to, because they do so many other things in a weird way.